Hi, my name is Chuck Althausen. I am a Senior Design Engineer for Advanced Adapters. This is my office. At Advanced Adapters, I am in charge of new product design, making sure that the product can be manufactured, and also we do quite a bit of testing prior to actually manufacturing the product, and once we get full production parts, we do some testing on that as well. For most of our design work, we use SolidWorks. The previous CAD software that we used is AutoCAD, so we're kind of making the transition currently to getting all of those old 2D parts into SolidWorks. So we're going to go through a quick demonstration of Atlas Exploded View in SolidWorks. We use SolidWorks primarily in the design phase because it allows us to visualize the complete product line, not only in a prototype sense, but it allows us to then take that prototype and put it to various transmissions. We can actually put it into vehicle solid models if people have that. We're trying to get to the point where we're a little bit more proactive in the sense that we can begin to start offering basic CAD models to people. In today's society, 3D computing is becoming so popular that it has a high benefit to people to be able to take a transfer case model to put it into their Jeep solid model. It also has the benefit of larger companies. I mean, they'll put it into their truck, their bus in a particular application. So for us to have high quality solid models that can kind of give us some understanding about how everything's going to go together, how everything is going to function in the vehicle is a huge benefit to us. Having SolidWorks is kind of only one piece of the puzzle. In the design process, while we do use SolidWorks for visual aid and design, there still needs to be calculations and stuff like that that need to support your design. I've always told people that say that they've designed something that I think that they're more creating a product rather than designing. I kind of define designing a product as iterating towards an optimized end goal where you're trying to optimize weight or cost or power intake. I mean, there's all these areas that you can optimize. I tell people all the time, you know, I can easily bring you in here and we can do a 10-minute tutorial. I can have you drawing parts on SolidWorks all day long, but once you've made that part, I mean, is it going to last? What material are you going to make it out of? You need to have a supporting drawing to support that solid model. If you give a solid model to a machinist, he doesn't know what's important and what's not important. So the drawing represents kind of almost a contract between you and the machinist. Here's the solid model, this is what I generally want it to look like, but this is what's important and this is what's not. And that would be information that you would convey on an engineering drawing. And that's one of the things at Advanced Adapters that we're trying to strive to do, is that we have well-documented engineering drawings that can be manufactured at any point in time, and the machinist knows exactly what to do. The quality control department now, and we just wanted to run over a quick summary of our gear measurement machine. This is kind of where all the aspects of design, manufacturing, this is kind of where they come to a head. This is where we prove that we are in fact hitting the tolerances and the quality levels that we are intending for our particular gears. At the end of the day, you can cut whatever you want to cut, but if you don't know what you're actually getting, then you're kind of shooting in the dark. As an engineer, once I finish a design and determine a particular quality standard that we need to meet, we then have to select materials and heat treat processes that we feel will meet those quality standards in the whole aspect of manufacturing the part. In this particular case, the MP205 gear, there's a host of materials that we could use for this. What exactly is right for the application is kind of dictated by how common is the material, how available is it, are there different diameters and sizes that you can make different size gears out of. So we're going to run a quick example gear here. This is a MP205 input gear. This is a OEM gear, so we're going to compare an OE gear to an aftermarket version that was cut overseas. This machine is a very accurate machine. It has to be in a temperature controlled room. There's a lot of aspects on gears that are very, very precise. Much of that accuracy is put into the cutting tool. But in regards to actually cutting the gear, there's three different areas that we actually have to measure. One would be the involute profile, that would be the surface of the tooth, and then in this particular case, this is a helical gear. We're measuring the helix angle and what the variation from a perfect helix angle might be. To kind of give you an idea of what the accuracy of this gear measurement machine is, if this was the cross-section of a human hair, which is roughly 2/1000ths, this machine has sub-micron level accuracy. It measures to the micron level, which is represented by this small dot on the 2000s hair. So we don't use all of the machine's accuracy, but it's there if we wanted to make very, very highly accurate gears. These little probe tips are rubies. They have to be much, much harder than the material that they're measuring. And generally when we're measuring a gear, it's in the heat treated state. So it's in the high 50 to 60 range of Rockwell. So the probe tip cannot wear down over time. It must maintain its shape at all times to accurately measure the gear. When we set out to manufacture an OE gear, we typically like to first check the quality level of the existing gear, and then from there we actually like to compare it to overseas copies. And in this particular case, this overseas copy of a MP205 input gear is roughly 2 to 3 quality levels less than the OE gear. From a design aspect, several quality levels lower result in a much, much lower duty cycle and strength of the gear. It may not look it from geometry wise, but subtle changes in the gear tooth represent a very high reduction in gear strength. So our goal with manufacturing 205 input gear would be to meet or exceed the OE standard of the gear to the best of our ability. So we're in the quality lab and we're standing next to the Rockwell hardness tester. This is where we determine if the heat treater is providing us what we specified on our engineering drawings to meet a particular quality standard.
This is the Ranger shaft that we did earlier, and now we're going to measure it on our gear measuring machine.
At Advanced Adapters, we're proud to say that we design, manufacture, and sell products made right here in the United States.